Welcome everybody to session number 7 of my lecture on statistical energy analysis and hybrid methods. After the treatment of the acoustic wave equation and acoustic waves, including field quantities like pressure, velocity, intensity and so on, we would now like to talk about sources, and we start with fundamental acoustic sources. Why are they important for SEA? Because this is the first step into how energy is introduced into acoustic wave fields. Because understanding the sources means how is the energy introduced into a cavity or to the exterior world surrounding an SEA model. Let's start. We start about this with a spherical source, and if we would like to treat a spherical problem, it really makes sense to switch to spherical coordinates. So our wave field, the space is no longer expressed in Cartesian coordinates x, y, and z. We're now using spherical coordinates consisting of a distance, an azimuthal angle phi, and a spherical angle theta. And these are the expression for the coordinate system. But what comes with such a coordinate transformation is that the space derivatives and the operators will also change. In this case, it will be the plus operator. We have a symmetric problem, so there is no angular dependence. So we're just interested in the Laplace operator in terms of the distance r, and the result or the definition of it is like this. When we enter this expression into our wave equation for the velocity potential, we will get this expression. So not the Laplace operator now is here replaced by the above expression. How can this be solved? The easiest way is to rearrange this equation, and that means that we will outfactor the distance r. And the wave equation then finally would look like this. The practical thing with that is that we have the simple one-dimensional wave equation here in the parentheses, which acts on r multiplied by the velocity potential. But what does it mean? It means that we can use any solution of the one-dimensional wave equation that we have that is a solution for this expression here. So we take an outgoing harmonic solution, because we are interested in waves that are radiating, so outgoing really makes sense, of this amplitude. We bring that the r on the right hand side, and this is the solution of our velocity potential for a spherical wave field. Good. So next step is to create an idea about a model. So what would be a good representation of such a source? And here acousticians very often talk about the breathing sphere. So we have a sphere of radius capital R, which vibrates with the velocity v index r. And how can we derive the velocity potential solution out of it? We know that the velocity is given by the negative derivatives of the velocity potential. We do this and we find the expression exactly here at the radius of the sphere, and then we get for A the expression that is given here. So not too complicated. Entering this into our ansatz, the velocity potential would look like this. Good. So the vibrating velocity of a sphere is a very artificial quantity, and in acoustic calculations normally another quantity is used, and this is the so-called source strength given by capital Q. And this is simply the volume flow rate. So that can be easily derived from this our sphere model by just multiplying the surface velocity by the surface of the sphere. And then we automatically get the volume flow rate and automatically get the source strength. This is here in time dependence expressed. If we move again to harmonic wave time dependence, we get a similar expression, and as usual we neglect the exponential function and just talk about complex vectors, and then we get this expression for the source strength, including a phase. Good. Entering this definition into our solution here on top of that and changing, also getting rid of the velocity, we finally get this expression for the velocity potential source strength. We have a 4 pi r expression and some terms that depend on the distance from the source plus the radius of the sphere. Let's have a look at typical solutions. We know there is a clear relationship of pressure and velocity from the velocity potential. I mean, it is defined as that. This is defined as that, and this is derived. And then we get a solution for the pressure and the velocity depending on the quantities that we discussed before. When we make a typical example as given here in the figure, here we have the pressure divided by the characteristic impedance and the velocity. We do so because in this case it fits into one diagram, as we know that the ratio between pressure and velocity is given by this characteristic impedance. And then we see that in the far field they are both in phase and they behave like a plane wave, more or less. And in the near field we have some slight phase difference of pressure and velocity that's occurring here in the near field of the source, and we will discuss this a little bit more. So let's check for some field properties. We start with the acoustic impedance. The acoustic impedance is a relationship of pressure divided by the velocity. Using the solutions from the last slide, we get this expression, and if we would like to separate this into the real part and the imaginary part, remember that's the resistance and the reactance, then we get this slope for both of them. So that means, for instance, let's have a look at the limit cases. So if the wavelength is much smaller than the distance, Kr becomes very, very small. If the wavelength lambda is much smaller than the distance, Kr is becoming very great. And what is the effect? Let's have a look at the resistance for the wavelengths much smaller than distance. We are approaching the characteristic impedance, so it is nearly a clear resistance, and the low frequency it goes to 0. And for the reactant is a different way. So we have much higher reactance here in the low frequency area, low Kr area, and then the high Kr area we are dropping down again, and the relationship between both of them is shifting. And if we do this mathematically, let's say we check what is the result of the impedance for the first case, we see that it is purely complex, and it might become very large if we get small r. And if we have the second case, that means we have a very small wavelength compared to the distance, then we see that we are approaching the characteristic impedance. So it means the wave field of such a spherical source is nearly like a plane wave. So this is what we call the far field effect. Good. So far for that. Now it's time to relate intensity and power to the source strength a little bit. To do this in detail, I would like to remind you to one expression that is quite important to understand this. The intensity, to give you, is half the real part of the pressure multiplied by the convex complicated velocity in r direction. You know that we have solution for pressure and velocity as given on the last slides, and this provides us an expression for the intensity, here expressed in terms of the volume of the source strength amplitude, or the root mean square value of the source strength. We can derive from this the total power. The thing is that we just have to multiply this via the integration surface. So then we integrate over the full sphere. So if we have a source somewhere here, it's not really a sphere, we integrate just over the full sphere to sum up to the total power, and then we get this expression for the total radiated power. So next step is to understand, okay, we can also use, let's say, derive an expression that relates the pressure to intensity and power. And first we start with the expression for the root mean square pressure, which is obviously given by this. And we know the pressure, and if we just check this expression and compare it to the first equation, we see that the only difference is that this is just squared here and here it is not squared, so pressure is just the intensity multiplied by the characteristic impedance. When we take this expression and divide it by the we express the intensity by the power divided by the surface, so going back a little bit again, then we get very simple relationship between the pressure and the power. So, which is okay, because we know there's a clear relationship between intensity and pressure, and that's also obvious that the farther we go, the surface that is getting bigger and bigger, and this means that the pressure is getting lower and lower the farther you get away from our point source. Okay, the next step is to introduce some, let's say, source quantities that will also be used later in another context, but it's quite easy to describe those in context of the spherical source. And the first one is the radiation impedance. It's the ratio of the pressure to the source strength. So we replace the velocity here by the source strength. The relationship is obvious. We just have to use the surface multiplied by the velocity to get the same expression, and we just know that this is the surface of the sphere, obviously. So that means we can also use, and this was by nature assumed, that there's a harmonic and constant harmonic surface velocity over the whole surface. So we get for the radiation impedance of a breathing sphere, and according to the acoustic impedance, exactly this expression. So we know everything, we know P, Z, and so on, and this is also an important quantity. The next step is the so-called acoustic radiation impedance. That's a very similar quantity. It's much more related to the impedance, to the acoustic impedance, because it's just the relationship of the pressure to the velocity at the surface. How do we get that? We just multiply by the surface, so we're just getting at the end, this is the remaining term, and this corresponds exactly to the acoustic radiation impedance of this. Don't panic about all those quantity. I will create some sheet on my website where you will find, let's say, where all those source and field quantities are summarized. So, why do we need all those impedances, source quantities, and so on and so on? I mean, one use of that is usually when we measure and when we describe a source, we barely have both quantities available. Normally we don't have pressure and velocity at the same time. Sometimes we know the pressure and sometimes we know the velocity. And by using those source describing quantities, we can get rid of one of those quantities, and that makes life a little bit easier. So just keep in mind, the power radiated source is expressed by this expression. So either we take pressure and velocity, then we need the surface of the sphere, or we directly switch to the source strength. Once again, another idea why the source strength is used, because just we have two quantities that we know to describe the source, and we don't have to know the source in this context, the source surface velocity in this context. So just I will show you two versions. So one is that I replace the pressure by an expression using the radiation impedance, and then we get this expression here. So just note, we just have the source strength and the impedance that gives us the power, or the other way around, we get rid of the source strength by using the reciprocal impedance then, and the expression would look like this. So we just have the measured pressure, or the well-known pressure, divided by the real part of the impedance, and then we got the radiated power. Please note, and this is why it's called resistance, why the real part is so important for the radiation. The efficiently radiated power always depends on the real part. This is the resistance. Okay, to give you an idea what this real and non-real and imaginary part of sources means, it's quite helpful to play what is happening at the surface of the sphere, and what is the impact of the radiation onto the sphere, which is actually what we are doing when we talk about the radiation impedances. So just imagine, just recommend Newton's law, and we express the force by the pressure and the sphere surface. And the acceleration is now expressed via the time derivative of the velocity in complex notation. That means multiplication by j omega. When we multiply this again via the sphere surface, we get this expression, and this part here now is converted into a term that is related to the source strength, which is exactly this part, as you know from the considerations from the slides before. So we derive the mass out of it here, and then we got exactly this expression. So we have this real part of this surface of the sphere divided by j omega, and pressure divided by Q, which is in fact the radiation impedance that we all know, and which is already given here. And if we think about, if we do the limit process for very small kr, we get this expression here for the mass. So it's 4 pi r cubed multiplied by the density of air, which is in fact 3 times the volume of the sphere. So that means if you have a very small breathing sphere, much smaller than your wavelength, the triple volume is moving around the sphere. It's not radiating, it's just moving. So what does it mean for the physical model of this reactance? And this is why it's called reactance. It's just pumping back and forth the fluid volume, but it's not radiating. This near field wave field, which cannot radiate, is called evanescent wave, because it's an oscillatory motion that itself doesn't radiate. So far for the sphere. Now we go one step further. We think that we have very small sources, and this is what we call point sources. That's what we have if we go for kr to the limit, so to very small values, it goes to 0. And if we do the limit process for all our solutions that I've shown before, we would get this for the velocity potential. The good thing is that it's now looking much simpler than before. Using this solution, we get also a simplified version of the pressure, which is given by this, and we get also much more simplified version of the radial velocity, which, if we further consider that r is much bigger than car, we would get this expression here. Good. We can also do the same limit process for the other derived, especially for the radiated power or the intensity. We will get this expression here, and for the power we would get this expression, which is again just the multiplication of this times the spherical surface. And when we use the radiation impedance then we could calculate the radiation impedance out of it, we would get this. That means that even the small, let's say a very small surface, we can define a radiation impedance. And again, we could not identify in this context here for this point source, we would not be able to qualify this quantity here, because we don't have a surface where we can balance the velocity. And this is also why it makes really sense to have a radiation impedance which is related to the source strength. Otherwise, you would not be able to create a radiation impedance quantity on a point source, which in the extreme limit does not have a real surface. Okay, so far for elementary sources. The next session 8 will deal with reflection and transmission of plane waves. We will investigate how waves are reflected and absorbed and typical, let's say, impedance conditions, and also how plane waves transmit from one fluid media to another. And this is very important for the surface absorptions of acoustic wave, which is very important for the damping in a cavity. And the transmission is a first hint on how we can calculate coupling loss factors, because coupling loss factors depend clearly on the transmission of waves or exchange of wave energy between two different wave fields. Okay, I hope you enjoyed this and see you soon for session 8.